In these next examples, we have glycerins, which is at 20 degrees C and is flowing within two parallel plates. And the pressure gradients is given by dpdx and is equal to minus 1.6 kilonewton per meter cube. So you are asked to determine the velocity and shear stress at a distance of 12 millimeter from the wall if the spacing B between the wall is given as 5 centimeter. And also, what are the shear stress and velocity at the wall itself, given that the velocity distributions for the viscous flow between the plate is given by that velocity profile. Okay, so first of all, of course, as usual, we draw a schematic diagram. Let's draw everything that we know. So that's the two plates, and given that the spacing is equal to B and is equal to 5 cm, and then here the fluid is glycerin at 20 degrees C, and then given that the pressure gradient is equal to dp by dx, which is actually a constant, and is equal to minus 1.6 kilonewton per meter cube, right? And this is the x directions. So this is the middle, right? So the velocity profile is given like that. So this is y is this way. So y equal to 0 here, and here is y equal to 5 centimeter, right? So at any one point, the velocity is equal to u, right? And the expression for u is given. So given that u, the velocity profile, or sometimes we use v, but in this case is use u minus 1 over 2 mu dp dx is just a constant. Don't have to worry about that. By minus y squared. Okay, so what are we asked to find? So find shear stress and u at y equal to 12 millimeter, right? Then also find shear stress and u at y equal to 0. This at the wall. Given u is minus 1 over 2 mu dp by dx by minus y squared, right? We are asked to find tau. Tau is actually the mu du by dy, right? So that's equal to mu. So du by dy, all these are constants, so I have minus 1 over 2 mu dp by dx. So I differentiate this, so I have b minus 2y. Basically, the expression for the shear stress is actually minus 1 over 2, because mu cancel, dp by dx, b minus 2y. So if you look at the chart for glycerin at 20 degrees C, so this is 20 degrees C, so we looked at, for glycerin, the value is here, so it's about 1.3 Newton second per meter squared. So mu from the chart for glycerin at 20 degrees C is actually equal to 1.3 Newton second per meter squared. So now we have obtained the expression for u as well as the shear stress. So what we need to do now is just put the numbers. So now at y equal to 12 mm, which is actually equal to 0.012 meter. So u y equal to 12 mm. So just substitute the value. So minus 1 over 2, 1.3 minus 1.6 times 10 to the power of 3. That's the pressure gradient. So 0.05. That's B, 0.012 minus 0.012 squared. So that gives us the velocity is equal to 0.281 meter per second, right? And then the shear stress for y equal to 12 mm, because this is the expressions So it's minus 1 over 2. dpdx is minus 1.6 times 10 to the power of 3. And then b is 0.05 minus 2 times 0.012. Right? So that gives me the shear stress is equal to 20.8 Newton meter. And then next you are asked to find the value at y equal to 0 at the wall itself. At y equal to 0, which is at the wall. Straightforward, u is actually equal to 0. Here, y equal to 0, this is 0, so u is equal to 0. And then the shear stress, tau y equal to 0 is minus 1 over 2, minus 1.6 times 10 to the 3, 0.05, so it's equal to 40 Newton meter, right? Okay, so at y equal to 12 mm, so it's equal to 20.8 Newton meter, whereas at y equal to 0, it's equal to 40 Newton meter. But generally, we can actually look from here by considering the velocity gradient here, right? Because shear stress is equal to mu dv dy or du dy, right? So if you consider the gradient here, the gradient is lowest here, means that 1 over gradient is highest here. So at the wall, the shear stress is highest, tau max here. Whereas here, the shear stress in the middle is actually 0 because the velocity gradient here is actually infinite. 1 over infinity is actually 0. So shear stress is 0 in the middle and maximum at the wall because the velocity gradient is very high there.